In this conservation of energy problem, you have a string with a mass in the end, and you let the string go, and it comes down in the circular arc here to its bottommost point, which I'll call point B. Call this point A here. But when it gets to point B, you can imagine the string coming down here, there's a peg. And the string catches on the peg, and so what's going to happen is the ball is going to come around in a smaller circular arc up here to point C, let's say. And the question you need to answer is, the questions are, what are the velocity at point B, the bottom, and the velocity at point C. So for this problem, conservation of energy problem, the first thing we're going to do is draw a reference line. So since the object goes down to this point B, I'm going to draw my reference line here right where the point B is. Note that as my reference line. Okay, so I draw it right on the diagram. So that's done. And so for part A, the velocity at B, I'm going to consider this motion from A to B. So it's an interval, beginning point, end point. So if I hold this thing here and I drop it from rest, I have no kinetic, but I am indeed above the reference line, so I have potential. There's no springs involved here, so I have no spring potential. When I get to the bottom here, B, I have kinetic, and I have no potential because I'm at the reference line, no gravitational potential, and there's no spring involved. There's no air resistance or any frictional forces, so I can ignore the work done by friction. So for part A, my equation becomes UGA, which is mg height at A, equals 1/2 mvb squared. And then I can solve for the velocity of B, because if I know the heights and masses, I can solve for that. Now for point C, and the distances between the pegs and all these things are known, I'm going to have a very similar situation. I'm going to have a velocity at B, and I can actually do this one of two ways. I can use conservation from A all the way to C, or I could say energy at B equals energy at C. I can use any one of those intervals, and either one should give me the exact same answer. So let me try the A to C method. So in the A to C method, I'm going to have to modify my buckets here a little bit. I'll erase what I had. Erase this bucket here, erase the energy here. Just make sure I put the energies in the correct slots. So for the second part here, this is going to be from A to C. So in A to C, what I have is, get my pen back. I asked myself, do I have energy at point A? Let's see, no kinetic. I do have potential, so that's the same. Could have left that there. And then these are now C's. And so I would say, okay, do I have kinetic? Yep, it's probably moving at point C. And if it weren't, and I were to calculate this velocity, I would get 0. So I would find out if it were 0 or not by calculating what it is. But I'll assume it's not 0. Is it above the reference line? Absolutely, it is. And there's no spring involved. So the equation for part B is mg height at A equals mg height at C. And again, I know all these radii and distances, so I can figure that out. Plus 1/2, it's a plus sign, plus 1/2 mvc squared. And again, given all the masses and all the heights, I can solve for the velocity at C. So here's a type of problem where we have motion from a high point to a low point, where we have gravitational potential energy transferred into kinetic energy, and then this peg is a little tricky part to it, but again, all we do is we consider heights from our reference line and velocities, and we can solve for the unknown quantities.